So welcome to this first lesson of the first week of the course Transformers, LLMs, and RAG and Agents. This course has a hidden complexity because it sits at the intersection of different disciplines. For one part, we have AI, the pure AI and machine learning discipline, which is really complex. And then we have software engineering, and then we also have DevOps and even security. And each of these disciplines is complex enough and can fill one person's career. But to develop production RAG agents and agents, we need to merge these disciplines. And so we need to focus in what part are we going to extract from each of these disciplines. For instance, we cannot delve in the intricacies of machine learning and all the equations and all the strategies and the theorems and everything that it entails. BSc AI Factory has other courses on that if you're interested. But we just will, in this case, we will just do a quick history about machine learning, about neural networks, and what are the characteristics, the takeoffs that we need as from the point of view of a software engineer to be aware of, so we then can use in the developments that we use. So it's not a pass for the user, it's a pass for the engineer that it then is going to take the characteristics of the machine learning model as a tool that we will integrate in our further developments. So it starts not 10 years ago with the transformer idea, not even in 2012 with the AlexNet and the introduction of GPUs in the world of machine learning. It starts in the 1950s, 70 years ago.
Look at this photograph. It is from around 1958. That machine is the Mark I perceptron, and it learns, not as a metaphor, an actual learning machine, more than 60 years ago. The ideas were in place for decades. The perceptron, 1958, practical backpropagation, the 1980s, convolutional neural networks, CNN, by the late 80s. What was missing for roughly 40 years was the ability to train them at a scale where they beat simpler, hand-built methods on real problems. They usually did not. So machine learning stayed a research field. Hold one sentence. The idea is old, the compute is new. Twice, the field froze. Roughly 1974 to 1980, and again 1987 to 1993, the two AI winters. Funding collapsed, confidence collapsed, because the results never justified the promises. Notice what was not the problem. The ideas were not wrong, the mathematics was not missing, the compute was not there. 40 years of good ideas that kept losing to simpler methods until the hardware arrived. Late 2012. Krzyzewski, Sutskever, and Hinton train a network called AlexNet on the ImageNet benchmark. The error rate falls from about 26% to about 15%. In this field, that is not an improvement. That is a discontinuity. And the architecture was not new. That kind of network was old. Something else changed. They trained it on two consumer gaming graphics cards. A graphics processing unit, a GPU, is at its core thousands of small processors doing the same arithmetic in parallel. That is exactly the shape of a neural network's training loop. The GPU put what used to be supercomputer class compute on a graduate student's desk, and NVIDIA's CUDA software layer became the foundation the whole field then built on. The lesson is structural, not historical. The architecture that matches the available hardware wins. The idea was old, the compute was new. That is the whole unlock. And this is not finished history, it is happening now, in two different arenas. At the frontier, large-scale training and cloud serving, the race is between NVIDIA's GPUs with CUDA and Google's tensor processing units, its TPUs. Closer to your own machine, local inference and fine-tuning, the contender is Apple's unified memory silicon. Different arenas, the same law. So when you meet a new model family, the first useful question is always, what hardware does this match? Here is the whole object with the mystique removed. A language model takes an ordered sequence of tokens and produces a probability distribution over the next token. Run it once, you get a word. Run it 1,000 times, you get a paragraph. That is the entire interface. Go one level deeper because it kills a misconception. That model is a program. It loads a very large file of numbers, the weights, and runs a long chain of matrix multiplications and simple nonlinear functions over them. One layer is essentially multiply by a matrix, add a vector, apply a simple nonlinearity. A network is many of those composed. Running it once is inference. Nudging the numbers so it comes out better is training. There is no reasoning step hiding in there. It is arithmetic on a fixed array of numbers at enormous scale. Now, the load-bearing idea of this whole course. The model predicts one token. That token is then appended to the input. The model predicts again. From the now longer sequence, the context only grows. The model is always reading what it just wrote. It is conditioning on its own output. Two consequences follow, and both will matter when you build. First, remove that loop and you do not get worse text. You get noise. Agreement between subject and verb, a clause that closes, a pronoun that refers to something. Those are feedback effects, not rules the model holds. Grammar itself falls out of the loop. Second, and we only plant this here, once the output runs past a few sentences, which coherent thing the model produces is largely decided by the early, probabilistic choices. A small difference near the start forks the whole continuation. We make that concrete in Lecture 2. For now, the loop is why the model is coherent. And the same loop is why it is not deterministic. Before 2017, the dominant sequence models were recurrent neural networks, RNN, and their steadier variant, long short-term memory networks, LSTM. They processed one token at a time. By 2016, they shipped real things: neural machine translation, short query speech recognition, the first smart reply. What they could not ship: long document understanding, because an RNN crushes everything it has seen into one fixed hidden state. By token 200, token 1 is gone. And industrial scale training, because they are serial. The field could see the ceiling. It had been pushing at it for years. June 2017. A team at Google Research publishes a paper titled, "With Some Confidence, Attention is All You Need." 3 ideas in plain language. 1. Replace recurrence with attention. Every token looks directly at every other token and decides what is relevant. No long chain to forget through. 2. Process the whole sequence at once. There is no serial dependency across positions, so all of them compute in parallel on a GPU. The architecture matches the hardware. 3. Stack the block deep. 12, 24, 96 layers, each parallelizable, so training scales. The first breaks the long-distance problem. The second breaks parallelism. The third breaks the capability ceiling. One operation bought all 3. You do not need the mathematics. You need the intuition. A noisy room. Someone says your name and your attention turns. You did not consciously check every voice. Something scored every source against, "Is this relevant to me?" and amplified the ones that scored high. Attention is that scoring, made learnable over tokens. The mechanism has 3 parts, named from databases. The query is what a token is looking for. The key is what each token offers. The value is what it contributes if it is chosen. Compare a token's query against every key, normalize the scores, take the weighted sum of the values. That is the entire mechanism, and we will keep it exactly at that depth. 3 consequences fall out, and these are the ones you will use. First, cost is quadratic in length. Every token is compared with every other, so a 200,000 token request is not 10 times a 20,000 token one. It is closer to 100 times. Second, attention is not uniform over a long context. The middle of a very long input is processed less reliably than its start or end. Third, every position computes in parallel, no serial bottleneck, and that is the property that let training scale. From the first two, a practical rule you will use in week 2. Put your reference material in the middle and the instruction you most need obeyed at the very end. This is the moment the story stops being one paper and becomes the technology industry. The killer app for AI. Take BERT, 2018. The interesting change is not the benchmark, it is what a project looked like. Before, a language task meant a bespoke pipeline, hand-built features, a task-specific model, weeks of work, deep subfield expertise, and poor transfer to the next task. After, you take a model someone else pre-trained, add a thin, task-specific head, fine-tune on a few thousand examples in an afternoon, and beat the old system. The skill moved from designing features to fine-tuning and evaluating a general model. Pre-train once, adapt cheaply. That pattern is the one this entire course rides. And then it left language entirely. Vision, audio, code, protein folding, which took a Nobel Prize. The same move every time. Adopt the transformer, retrain on the domain's data, win the benchmark, replace a decade of bespoke engineering in about a year. The convergence is the story.
And yes, I'm sure that you have heard about the transformer and about this paper, Attention is All You Need. I don't think that you have read it, but it's important. But why it's important? Why it's a breakthrough? And I would like you to think about the history of physics and sciences. There was a moment at the end of the 18th century, the moment that Sir Isaac Newton writes the Principia Mathematica. In the Principia Mathematica, Isaac Newton determines the way of how science should be performed. He shows the equations, he gives us calculus, he shows us how we can record and systematize and turn into mathematics the experiments and the measurements in the lab, and then we can formulate mathematical laws. And then what happens is that after a few centuries of Galileo and Kepler and so on, working in their different disciplines, and then everything merges into one language of science. Everybody can read each other's papers because they all use calculus as the way of communicating their research and their predictions that can be validated in what we call in this process of science. You make a prediction, you formulate a law, and then you can make other experiments, and then you can make comparisons. This universal language of science made that everybody could work together and we could build science one on top of another. It's not one breakthrough here, one breakthrough there. It's just one linear progression, and then we get the international measurement system, and we get all the laws that we study when we study physics and chemistry and so on, because we all can build one on top of each other. In the world of machine learning, in the world of artificial intelligence, attention is all you need. The transformer idea is such an idea. It's like one universal way of creating and designing neural networks. And it's not just this idea, is that it's accompanied by code, and of course open source code and data sets that are prepared to be used like that. So everybody that is in the game starts working together. People that 10 years ago couldn't read each other's papers and understand each other's theorems, then now everybody works in the same field, in the same way, and all the developments in the world of machine learning start to compound. It's not breakthroughs, one breakthrough here, one breakthrough there, unrelated. Every minor improvement is improvement, the results and the technology of everybody else. So the field starts compounding really rapidly. So we can get to 2020 and 2022, especially with advent of GPT-3, which is the last breakthrough that gets software engineers involved in the thing.
In words, an encoder is a reader. It takes the whole input at once and builds an understanding of it. Good for judging, classifying, finding. BERT is an encoder. A decoder is a writer. It emits one token at a time, each conditioned on everything before it. Good for producing answers, chat, code. Decoder only models one conversational AI, and the reason is the objective, not architectural purity. Predict the next token of any text is the most general task you can set, so the entire internet becomes training data. The breakthrough is GPT-1 in 2018. GPT-3, 2020, is the moment it became undeniable. Around 2020, a quieter result. Scale the parameters, the data, and the compute together, and the model's error falls along a smooth, predictable curve. Capability became a forecastable function of money spent, the closest thing this field has to Moore's law, and, like it, an empirical observation, not a theorem. Three things followed: claims of sudden emergent capability, a bankable business plan, about $500 billion of infrastructure raised against a chart, and a real bubble risk, because that spending has run far ahead of revenue. The substrate is stable, the business climate on top of it is volatile. Engineer for both. But scale alone is not the model you call. A pre-trained transformer at scale is GPT-3. It continues text. Ask it for the capital of France, and it might continue with more questions. What made it usable was a deliberate engineering turn, instruction fine-tuning, then reinforcement learning from human feedback, RLHF. Humans rate outputs, and the model is trained to prefer what they rate highly. RLHF is why the scaled model became an assistant. We name it here. Lecture 2 takes apart how it works, so hold the whole shape. The modern large language model, LLM, stands on three pillars: architecture, in 2017, scale, in 2020, alignment, in 2022. Take any one of them away and you do not have a usable modern model. That is the mental model the rest of this course is built on. 6 things to keep. 1. The modern LLM is 3 pillars: architecture, scale, alignment. 2. It won by 3 coincidences, in order: the GPU revolution, the transformer, the scaling laws. 3. A network is weights plus arithmetic. No reasoning hides inside. 4. Attention is quadratic in context length. A long context is far more expensive than it looks. 5. Generation is one token at a time, and that loop is why the output is both coherent and path-dependent. 6. One architecture unified the whole field, and that is why progress now compounds.
So here ends the first lecture. In this lecture we have covered a lot of ground, a lot of history, and our sweep has been shallow, but there we have been stopping in a few takeouts and in a few ideas that you will need to remember and to integrate in your understanding of the field as we move forward. Agent development, which is the main topic of this course, is not going to involve designing machine learning strategies or fine-tuning or training. None of that is going to matter for us, because we're going to use LLMs as one of a closed tool. We will use several LLMs and we will use it in different ways. We need to understand how to use it. Building agents involves a new set of complexities that sometimes is overlooked by the machine learning community. But right now it's really complex to create proper agents, and to create an agent and create useful tools that we can then apply to real world problems. Then we need to understand what are the capabilities, the limitations, the costs, the scalability issues, and everything around LLMs as a closed thing. We have to understand attention, we have to understand tokens, we have to understand costs, we have to understand performance, and then we can build our tools on top of it. So now you have available to you the first exercise. This exercise is going to involve you creating an account in Hugging Face, which is like a hub, worldwide hub, like GitHub is, but for machine learning models, then and LLMs and tokenizers and a lot of things. And you need to create an account, and then you will get an API key that will allow you to run models on your computer using a Python script in this case. In this case, you're going to run tokenizers and you will have to make some observations. Last but not least, in the materials of the course, we're going to propose you and provide you with a guide to set up an Ubuntu virtual machine in your computer. Why do we propose you to use an Ubuntu virtual machine? So we all have the same setup, we all have the same paths, we all have the same way of working with the exercises and the materials of the course, so we can provide you with the same commands and tools. If you, for instance, want to use Windows, you're welcome, but we are not going to give you support, and the way Windows works in the terminal and it works with UV and works with Python and other things is not standard. So it's better to use a virtual machine, and then we will have all of us will have the same setup. Also, when we start building agents and we start trying risky things like providing tools and terminal access to our agents, it will be safer if we have our agent enclosed inside a virtual machine. So my suggestion, please, if you can, dedicate the time and follow the instructions that we will provide you to install a virtual machine in your laptop or in the computer that you will use. We will have, for this first week, we will have a synchronous or present session. We will inform you when the class is, where the class is, and then this first class is going to involve a lot of support from our part, because all the questions that you have from the exercises in these first lectures and the lectures of this first week, we will provide you with support so you don't get stuck. You also have, remember, in the forum, in the course, you have a forum. You can ask questions. You can say, I didn't understand this. We would like more information about this. Can you provide, Mark? Can you provide more references? Can you provide another, podcast videos where you can provide further information, because I want to learn specifically about this. Then we can provide you lots of information. Our mission is not to provide you with all the information, but to curate what information we provide to you and how to pace it so you learn the best. So I hope you are finding this interesting. We'll see you in the next lecture.